Okay, these are the review slides. They're on the end of the PowerPoint that's titled Mole Mass Relationships. And let me get the chat visible so that I'm sure we'll have questions as we go. Whoops, that's not. Okay. So we answered some of these questions about diatomics, Lewis structures. I know the one Lewis structure I didn't do in either one of the lectures from yesterday was this number 3. So why don't we just try to draw this out? I think this one's not going to be too tough. 3 carbons, 6 hydrogens. You got 3 oxygens though. So you could probably draw this several different ways. But go ahead and attempt to draw that out. Remember that carbons always make really good central atoms. And oxygens always have to have 2 bonds. So I'm just going to start kind of connecting a few things. Wait, I want to make that a carbon. So you could put your 3 carbons in a row. And then I don't know, you could, what if we did like 3 OH groups? I mean, this is just one option. That way you got your 3 oxygens. There's 3 hydrogens. Is this going to work though? I'm not sure yet. Remember, you always have to make sure carbons have 4 bonds. So we only have 3 hydrogens left to account for. And if I throw these 3 hydrogens up on the other side, then I have an issue with my last 2 carbons. You see that? Those 2 outer carbons only have 3 bonds each. So I can't do that. I got to try something else. You know what I would actually like to do? I'm going to edit this kind of in a bigger way. I'm going to put an oxygen in between some carbons. You can totally do that. You could do carbon, oxygen if you wanted. That way I leave some more space for, let's see, now I've got, this may not work out either. If you got to put 3 bonds on this. There's 4, 5. Yeah, that's not going to quite work either. What if I do, let's see.
Could you do a double bond with oxygen? Like if you put, yeah, okay.
You're probably going to need a double bond somewhere. What if we tried that? I like that idea from Rachel. And we've got 1, 2, 3, 4. And then what if we put a hydrogen there? That's 5 hydrogens. So that carbon's good. And I got one more I can put right here. There's 1, 2, 3, 4, 5, 6. So this one was kind of a little bit more of a challenge than I anticipated. But I think it's a really good exercise because you can see even I have to erase and try different things. Okay. I'm not necessarily going to get it the first time. And just remember that with Lewis structures, don't freak out on the exam. If you try something, you're like, oh gosh, I'm wasting time. You should have plenty of time. Oh, did you get, somebody was holding up you should have plenty of time to work things out, even if you have to erase and start all over. Okay. Sometimes that's just part of it with Lewis structures. So anybody have another structure they drew that was totally valid for this one?
I think mine's a little different. I don't know if you can see. I can't even see myself, so I don't know if you can see this.
You gotta hold it like
bottom one right there.
Hold it closer. Bring it even closer.
That's what I did, Kylie. Like that exact thing.
Okay, so you have 3 carbons in a row, and then you got a double bond to an oxygen on the end and an OH. So you got 3 carbons in a row. And then you got a double bond to carbon there. And then you got an OH on that one. And then you got an OH on the middle one. Okay, I think we got it. And then the rest got to be hydrogens. Is that right? Like this?
Yeah, I put the rest hydrogen.
All right, what about this? I don't know if you can read that, but.
Bradley, okay, Bradley, hold it a little closer. I gotta make the screens bigger somehow. Okay, so you've got carbon, carbon, carbon. 1, 2, 3, 4, 5 hydrogens. That's good. And then, okay, 1, 2, 3. You just put those 2 oxygens on the end there. That works. Every carbon has 4 bonds. Every oxygen has 2 bonds. Yeah, that's doable too. So several ways you could draw this one out. And again, if you run into one like that on the exam where you're like, I think I could do this multiple ways, I will count any way correct. I'm not just going to count one way correct. So number 4 we did in I think the 10:50 lecture. So if you were in the 8 a.m., we didn't go over this one, but this one you have a C. This one's kind of written out more like a condensed structure, but we realized there was a typo on this one too. You had to put this oxygen in parentheses. So we had a CH3 group and then a carbon, and then we had to have the oxygen branched off. Remember, if it's in parentheses, it is branched off the preceding central atom or main chain element, which is that carbon. Then you got an OH group there. So that is what this one looked like. And I think this was actually very similar to the structure that was on the Kahoot game. And I said, name the geometry of that second atom, which should be, or that second carbon, which was trigonal planar, right? How do y'all feel about molecular geometry? Y'all feel okay with that? Okay. Well, I hope so. This was a problem we worked in lecture that was directly regarding molecular geometry. And I had to just fly through it in the 8 a.m. lecture. So we had a little more time to slow down in the second lecture, but the key to this is you have to see the Lewis structure to draw it out. And then the other key is you have to correctly count your charge clouds. All these structures have single bonds, but remember, double and triple bonds you just count as one charge cloud, or you can count them as bonded atoms. How many atoms are bonded to my atom that I'm naming the geometry for? So what I want to pick up with though is this question right here. Which molecule contains only 2 unshared pairs of electrons? So you're going to draw out the Lewis structures, and any molecule that has 2 unshared pairs of electrons, you would circle that one. So water, you should have the oxygen with 2 hydrogens. And we know oxygen is 2 bonds, 2 lone pairs. So that fits, only 2 unpaired shared pairs of electrons. Oxygen there has 2 unshared pairs. So A is a good answer. What about B? We've got nitrogen with 3 hydrogens attached. And then we got a lone pair. This does have a lone pair, but it's only 1 unshared pair. And then you've got BeCl2, Be beryllium, Cl. These chlorines have like tons of lone pairs, right? So that's 6 unshared pairs of electrons. So that does not fit. And then Mg, double bonded to oxygen. And that one should also have 2 unshared pairs. So A and D actually both fit there. All right, that's that one. The next one, we're getting to kind of some polarity stuff. So definitely expect questions about polar bonds and polar molecules on the exam. So this one, which bond is the most polar bond? So if I ask you something like this, we need to think about the table that we use to classify bonds as polar. I'm going to jump over here to this lecture from chapter 4, and I'm going to scroll down to the slides where we talked about polarity and where we had the electronegativity chart, and we had this little table right here where we classify bonds as polar. So as electronegativity difference increases, this little quote, where was our quote? Oh, the larger the electronegativity difference, the more polar the bond is, okay? So a non-polar covalent bond, that's gonna have the smallest electronegativity difference, and then polar bonds have even bigger electronegativity differences between their atoms. Ionic bonds have extremely large. So on this question, if you have a bond that is non-polar and then polar and then ionic, the one that's ionic has the largest difference, and you would actually list that as the most polar. It's so polar that it's ionic, but if you have one that's ionic, that's going to have to be your choice because it's the electronegativity difference is bigger than any of your polar and non-polar bonds. So, all right, so we have CBr So what is the difference there? I know carbon is 2.5, and I just know that from doing this so many times. Anybody have electronegativity chart they could look at? So I don't have to flip back and forth between slides a time. I know fluorine is 4.0, so this one's going to be 4.0 minus whatever boron is. Lithium and fluorine, that one's going to be 4.0 minus whatever lithium is. And then phosphorus minus, and then bonded to the chlorine. Anybody have the chart? Anybody? Okay, bromine, Kyle's bromine is 2.8. So we got 2.8 here minus 2.5. So that's a difference of 0.3. What is boron? (2.0), and Danielle says lithium is 1.0. Okay, so this one's 2.4 minus 2. So this one's going to be a difference of 2.0. So that's really, really big. It's ionic. Lithium and fluorine. So that's 4 minus 1.0 because Danielle said lithium is 1 on the electronegativity chart. So that's a difference of 3. That's huge. And then what about phosphorus and chlorine? Phosphorus is 2.1. Chlorine is probably going to be like a 3.5 or something. So Kylie says there's a difference. Okay, 3.0. So we got 3.0 minus 2.1, and Kylie says there's a difference of 0.9. So obviously the one that is the largest electronegativity difference, it's asking the most polar bond, is going to be this, well, I meant to highlight. Going to be this lithium fluoride bond, okay? It's a difference of, that's the biggest difference, 3.0. So even though you're like, but that bond's not polar, it's ionic, you're right. But we classify polarity based on electronegativity difference. So you'd pick the one with the largest electronegativity difference. Okay, now which molecules are polar? I think these questions are sneakily hard. Like they don't see, because you don't have a lot of math to do, but there's just a lot of layers and steps. You got to draw the Lewis structure. You got to figure out which element is least electronegative, which one's more, and draw in your dipoles and all that. So we've got sulfur here with lithium on each side. All right. And obviously lithium's the metal. It's going to be the least electronegative element. Lithium is main group 1. If you're looking at a periodic table, sulfur is main group 6. So if you're going to draw in the partial positives, you're going to put those on the lithium. And if you're going to draw in the partial negative, you're going to put that on the sulfur. So this one is going to have, how we're going to draw the dipoles in. Remember, you always draw dipoles in from the partial positive side pointing to, and you've got lone pairs on the sulfur. I forgot those. You've got the arrows pointing towards the partial negative side. Remember, there were 3 things we said you have to consider when you're deciding if a molecule is polar. I'm going to jump over to our chapter 4 slides and remind you of those 3 things. After we talked about polar bonds, we said, okay, polar molecules. Number 1, do you have polar bonds? Yeah, the sulfur lithium bonds are definitely going to be polar if you look at the electronegativity difference. Do you have lone pairs? Yep, we got lone pairs on the sulfur. But what about the shape? What you notice with the shape is that your 2 arrows here are pointing towards one another, okay? So these actually do cancel out. And I need to explain this because some people might say, okay, think about a molecule. Well, hold on. What molecule should this remind you of? Whoops, I wanted black. It's actually water. That's exactly what I was going to say, water. And we know water is technically, but you see me draw water like this all the time, okay? And because it's bent, if you look at the geometry of oxygen, it's bent. And so when we draw those dipoles in, they're actually slanted like this. And that is very, very nuanced and confusing here, because if we draw the lithium and the sulfur like this, we're going to tend to, I bet a ton of people would tend to think, okay, these are pointing in the, they would tend to think, like I just said, oh, these are going to cancel. But the molecule geometry for this sulfur here is actually bent just like water. So we have to treat it the same way. So again, the rule you need to go by when you're looking at these things is if the arrows are pointing in the same direction, they do not cancel. So sorry what I said earlier, they do not cancel. If the arrows are pointing in opposite directions, then they do cancel. But if they're pointing in the same directions, they do not cancel. The arrows are pointing opposite directions like this, then they do cancel. Boom, boom. If they're pointing in the same direction, like this right here, they do not cancel. So how do we know if it is bent or not? Well, Whitney, if we looked at charge clouds here, I see I've got 2 bonded atoms, lithium and lithium. You could also just count the bonds if you want. 1, 2 right there. And I've got 2 lone pairs on this sulfur, one right here, and I've kind of scribbled a lot down here, but the other lone pair is right here. That's 4 charge clouds, okay? 4 charge clouds, 2 lone pairs, I'm gonna abbreviate, and 2 bonds. That is a total of 4 charge clouds, right? So if we go to the geometry chart, that is also chapter 4. I'm gonna go over to that table. I gotta scroll up. Right up here. Here it is. So if you have number of bonds or number of bonded atoms, if it's 2, and then you have 2 lone pairs, that's 4 charge clouds, that corresponds to bent geometry. Does that help answer your question, Whitney? So this one actually, okay, good. This one is polar. The dipoles do not cancel out. But this one's, I think it's tricky because you would be tempted to say, oh, those arrows do cancel because they're pointing the same way. All right, NH3. So then we got nitrogen with 3 hydrogens. We got a lone pair, okay? Nitrogen-hydrogen bonds. Are these bonds polar? Nitrogen is I need an electronegativity chart. Do I have one right down here? There it is. Nitrogen is 3.0 if you're looking at this chart. Hydrogen is 2.1, so that's a difference of 0.9. So all of these bonds are polar. Okay, so these are all polar bonds. And we
Okay.
have, oh, go ahead,
So
Brad.
how do you determine like which method you use to figure it out?
All I'm doing is I'm walking through those 3. Let me scroll back down. I draw the Lewis structure. That's always the first step. And then I'm gonna walk through, here it is right here. I'm gonna walk through these 3 determining factors. Do I have polar bonds? So we said the lithium sulfur bonds are polar. I didn't actually calculate that for the lithium and sulfur, but I know because you have a metal and a non-metal that those bonds were polar. So hydrogen and nitrogen are 2 non-metals. So I tend to definitely go to electronegativity chart if I have 2 non-metals and make sure that my bonds are either polar or non-polar. But anyways, I'm looking for polar bonds. So I assess what kind of bonds I have and if those are polar or not. Then I look at my structure, Bradley, and I say, okay, do I have lone pairs? Yes, I do, right here on the nitrogen. So why do these things matter? If you have polar bonds, remember, these bonds between hydrogen and nitrogen means that the electrons in those bonds are not shared evenly. They are pulled, these electrons are pulled towards nitrogen in every bond if it's a polar bond. Okay, and so because of that, you can draw in the partial positives on hydrogen and partial negative on nitrogen. And especially knowing you have a lone pair there, that's a region of a lot of it's electron dense. Okay, there's a lot of negative charge there because there's a lone pair there. All right, so when you can draw separation of charge like this because you have polar bonds, because you have lone pairs, the last thing you have to assess is, do I have symmetry? Do I have symmetry such that my dipoles cancel out? Because I guarantee you, yeah, you'd be like, oh, there's symmetry right there. But is it symmetry that causes your dipoles to cancel out, if that makes sense? All right. And here the dipoles didn't cancel because they're pointing the same way. If they're pointing opposite ways, it's when they cancel. I know that is really nuanced. but that's how it is. So here, because you have lone pairs, because you have polar bonds, now we can draw a dipole in that is pointing from, I mean, you could draw 3 if you wanted. 1, 2, 3. You don't have to draw 3, just 1 would suffice. Okay, but you can draw dipoles in and none of those dipoles cancel. I know this looks really messy. I'm sorry, but does that help answer your question, Bradley? Does that help kind of give you a method to do these with?
Yes, I think so. Okay, so that's a polar molecule, correct?
Yes, yeah. So this one is polar.
I was wondering the same thing Kylie said in the chat. Does the one that gets the negative the highest electronegativity always? Okay.
Yep. So you can go to your chart too, that electronegativity chart, and say, oh, I know nitrogen has a higher electronegativity value than hydrogen. So I'm going to be giving these elements that have the higher electronegativity values the partial negative, and hydrogen the partial positive. But also make sure it's a polar bond. Sometimes you got an element over here like carbon and hydrogen, but remember the difference between carbon and hydrogen is 2.5 minus 2.1. That's actually a difference of 0.4. So that bond's not polar. Even though carbon's halfway across the periodic table, I would not put a partial positive and a partial negative on a carbon-hydrogen bond. So just always make sure it actually is a polar bond based on the number difference.
So if you gave us like a question like that on the test and it wasn't polar to begin with, like we would just put like no, like it's not polar. Like we wouldn't have to do all this work.
Oh yeah, Madison, if you can tell like you got if you've got a molecule of oxygen, right? And you look at that and you say, well, even though I have lone pairs all over this thing, any atom bonded to itself, the electronegativity difference value, that's 0. So that's a nonpolar molecule, even though you got things like lone pairs and oxygen's a really electronegative element.
Okay.
I'm reading in the chat. So Riley said, so does the molecular geometry determine where the dipoles point to? Riley, it helps play a role. The reason I brought up the whole water molecule thing down here is because when you draw it in an actually bent shape, it kind of helps you see that the dipoles don't cancel out. But that's why I wanted to bring up the point that if the arrows are pointing the same direction, even if they're like on the same plane and it looks like they would cancel, if the arrows are pointing the same direction, you can say they don't cancel. But if the arrows are not, if they're pointing opposite directions, hopefully that's an easier way to tell. Molecular geometry can help for just drawing the structure out, but it doesn't necessarily determine if your molecule is polar or not. There's other, it's like one piece of the puzzle. There's other things that play into that. Does that help answer your question, Riley? Okay. Whitney said, I'm sorry, do the arrows point towards the sulfur? Yeah, these arrows, if you're asking about this lithium sulfide molecule, those arrows do point towards the sulfur.
So, I didn't mean to interrupt, but okay. So I don't know if you are able to tell us this yet or not, but do you think for the test, like it would be whole questions almost? Like, is it polar or where, like, would you ask like specific, like which element does the dipole or kind of like both?
No, I'm not going to get that. I'm just going to say, which are any of these polar? Are they non-polar? Things like that.
Okay.
Because Rachel, we have talked about it in detail, but I tend to realize, and one of the biggest complaints about chemistry classes, people will say, the exams are so much harder than the lectures or the homeworks. And they probably feel harder because, you're timed and you're trying to do it on your own. And there's a lot of other factors that play into that. So I have tried to make sure my style of questions are the same as what we're talking through when we're doing normal lecture stuff. I can't always guarantee that that's going to be perfect, but I'm not going to get nuanced and just say something crazy specific that I haven't ever asked before, if that makes sense, Rachel. Yeah. Let me catch up in the chat. Kylie said, would CH4 be nonpolar? Yes, it would. It's covalent, absolutely, Kylie, but nonpolar. Covalent because the electrons are shared in all the bonds. non-polar because none of those bonds are polar. Whitney, the partial negative is what I meant by that. So you're saying, let me make sure, Whitney, yeah, the partial negative is on the sulfur. Okay. Okay, all right, I think we're good, caught up in the chat. So if we're continuing over here, C2H3Cl. So if we're drawing a molecule like this, we've got carbon and carbon. We got 2 carbons. And we only have 3 hydrogens here and 1 chlorine. So this molecule, what are we going to have in this one? If I if I put all 3 hydrogens on 1 carbon, and then all I can do is put the chlorine. I can't draw it like this because that second carbon is very unsatisfied. Maddie said it, double bond. So you got to double bond your carbons here. And then you got hydrogen, and then you got hydrogen off that one and chlorine off that one. So now looking at this, if you have brain space to memorize, never are carbon hydrogen bonds polar. They're always nonpolar. Okay, that one might save you some time trying to calculate things. So I'm looking at this molecule. Again, what Bradley hit on earlier, what's the method? We drew the structure. Now I'm assessing my bonds. What kind of bonds do I have? I see I have carbon-carbon bonds. Are those polar or nonpolar?
They're non-polar.
Yep, identical elements there, so non-polar. And all these carbon-hydrogen bonds are also nonpolar. Okay, what about this carbon-chlorine bond? That's the only other kind of bond that I see. We're looking at the electronegativity chart down here. 2.5 and chlorine is 3.0. 3.0 minus 2.5 is 0.5. So it's barely polar, but it is. So we do have 1 polar bond right here. And where am I going to put the partial positive? Because we have a separation of charge.
The carbon?
Yep, right there. And then the partial negative goes on, you got all these lone pairs on that chlorine as well. So now we draw the dipole in, pointing from the positive towards the negative. So that is a polar molecule because that doesn't cancel out with anything. If you consider the shape of this molecule, there's no symmetry, doesn't cancel. So this one is polar.
So all it takes is one of the bonds. Okay.
Yep. In some cases, just 1 polar bond can make a whole molecule polar. But you got all these lone pairs too on that chlorine, so that's contributing as well. Okay, CCl4. Carbon, what this looks like is the 4 chlorines. Okay, we just said that a carbon-chlorine bond is polar. Okay, we just identified that in the previous molecule. So all of these bonds are polar. So if I'm going to write the partial positive and negatives in, I'm going to put the partial positive on this carbon and all of these chlorines are drawing the electrons in the bond with carbon towards themselves. So now we start drawing dipoles in. We got to draw a lot of these because you got all these different bonds. So 1 to that, oh, sorry, I didn't mean to put 2 on that chlorine. 1 out this way, 1 going up, and 1 going down. And what you notice, remember, if arrows are pointing towards each other, they don't cancel. If arrows are pointing away from each other, opposite directions, they do cancel. There's all kinds of symmetry in this molecule. So every single one of these dipoles, the up and the down arrows, those cancel. The left and the right arrows, those cancel. So this molecule overall is non-polar. Okay, how do you guys feel about polar molecules now? I'm telling you, I think this is some of the trickiest stuff. Again, not because it's like, I'm not doing calculus here, but there's just a lot of different steps.
You're deceiving.
Deceivingly difficult. Okay, so there's that one. We'll move on to the next question. This one is write and balance the following equations. Solid calcium hydroxide reacts with aqueous hydrogen phosphate, that's a polyatomic phosphate, to form calcium phosphate and water. And then once we get that written and balanced, the next thing says we're going to classify the above reaction as redox, acid, base, or precipitation. Okay. So we've got calcium hydroxide. What's the formula for calcium hydroxide? So if you're looking at a periodic table, do I have one on here? No. Here's what I know. Calcium is main group 2. So the charge on any cation, okay, Maddie gets us almost all the way there. She said, okay, Danielle, thanks. It's Ca, that's calcium. We got hydroxide, OH. Calcium is a +2, hydroxide is a -1, so we've got to have 2 hydroxides. The only thing, Danielle said it in the chat, the only thing her formula is missing is you've got to have parentheses because this is a polyatomic ion. And when you need more than one, you got to put it in parentheses. If you don't, it looks like you just have 2 hydrogens, not 2 hydroxides. All right, calcium hydroxide reacts with, whoops, and this is a solid, reacts with aqueous hydrogen phosphate. So I'm going to write it up here. Hydrogen is this, obviously, right? Phosphate is PO4. What's the charge on phosphate?
-3.
-3. So what does the formula for this look like? H3PO4 is what Kylie said in the chat. That is correct. You can do the switch trick if you want. Or if you figure out another way, that's what you need. Okay. Then it says we form calcium phosphate and water. So calcium is going to bond with phosphate. So what is the formula for calcium and phosphate put together? Again, calcium is a +2. Phosphate is PO4 -3. Got to write something that is charge neutral overall. Switch trick. Volunteer the switch trick. I like that. Let's do Ca3PO4 2. I like it. There it is. Kendall said it. Thank you. And then we're going to get water. Okay. H2O. Water is a liquid. Okay. So what do you guys think? Does this look like acid base, redox, or precipitation reaction? Danielle said acid base. Mackenzie said acid base. Okay, so acid base always, one product of an acid base reaction is always water, right? And we do have water on the product side over here. Here's what else I noticed is that we have a metal hydroxide. And then we have an acid. How do we abbreviate acids? Do you guys remember? I'm gonna scroll over to right here, this slide right here. Bradley, this is gonna help. We abbreviate acids as right here, HA, because acids donate hydrogens to other compounds in solution. And then we have a metal hydroxide. So this is a very generic form of an acid-base reaction. It yields water and some kind of a salt, which is the metal cation from your base plus the anion from the acid. Remember, we broke up the acid into an H+, and the rest of the acid, whatever it is, the anion part, here the anion part of the acid is phosphate, is going to combine just like it's a double displacement reaction. Okay, the H+ from the ion, or ion from the acid combines with the OH ion from the base to give neutral water, and then the anion from the acid combines with the metal cation to give the salt. And that's exactly what you have going on here. You got the hydrogen, the anion part from the acid. So this is your acid. This is your base. And you're forming water, and then this is your salt. It's the metal and the anion part from the acid, which is the phosphate. Okay, so this is definitely acid-base reaction. Questions on that? Okay. So moving on. This one, you're given a reaction. It says balance the chemical reaction in the redox reaction above. So I'm telling you it's a redox reaction. Which element is oxidized and which element is being reduced? Which element is oxidized? Which element is being reduced? Okay. What do you guys think? Here's something I automatically notice if I'm looking at the reactant and the product sides. I see something that's by itself. So remember the rules for signing oxidation numbers are right down here. Number one, an atom in its elemental state, meaning by itself, has an oxidation number of 0. So this chlorine right here should get an oxidation number of 0. That's the only one by itself, though. So that's the only easy part. Let's just start going through. Mn, what is Mn? It's not magnesium. Magnesium is Mg. Mn is manganese. It's a transition metal. Okay, so what oxidation number would you give manganese? Remember the sum of the oxidation numbers for manganese plus the sum of the oxidation numbers for oxygen, they have to add up to 0. So what do you want to give oxygen? What do we want to give manganese here? Kylie, two on what? 2 on manganese. Let's try that. We would give a +2 here. Then what are we going to put on oxygen? We give a -2. But here's what I notice. I've got 2 oxygens. So that means I got -2 and -2. That does not add up to 0, right? So what if you make manganese? Kendall said try a +4 in the chat. If you make manganese a +4, now does that add up to 0? If oxygens each a -2? It does. So we've got oxygen as a -2. I'm going to erase some of my equation stuff. I'm just going to write in the oxidation numbers. Oxygen, and you're talking about an individual oxygen anion here, or atom, is a -2 oxidation number, and manganese is +4. Okay, let's slide over to HCl. What do you want to give hydrogen? What do you want to give the chloride? Okay, I'm seeing +1 and -1 in the chat. Okay, now let's move over to the product side. Here I've got manganese with 2 chlorines. So remember the sum of the oxidation for manganese plus the 2 chlorines, they've got to add up to 0. Kylie, remember the first element gets the positive oxidation number. The second element always gets the negative. So we've got to put a positive on manganese and a negative on chlorine, but think about what numbers. Maddie says a +2 on manganese. Okay.
Could you do the same thing that you did for manganese and oxygen, or no?
What do you mean? Like
the +4 and -2?
If we put, Rachel, if we put a +4 on manganese, like what it had on the other side, here's what I know about chlorine. Chlorine's a halogen, main group 7. As an anion, chlorine always carries a -1 charge. So if I've got -1 on chlorine and I've got 2 of them, I've got -1 and -1. And that doesn't add up to 0. Okay, so chlorine is a -1 here. Manganese is a transition metal, and those we know can carry different charges. Okay, that's how transition metals are. That's why they're difficult. And so manganese has to be a what here? I think, yeah, I'm gonna go back to what Maddie said. If we keep that +2 there, and each chlorine has a -1, now everything sums up total to 0. So I'm gonna erase all the equation part. I'm just gonna keep the oxidation number for individual chlorine and individual manganese. All right, now we go over to water. What do we want to give hydrogen and oxygen? I want to hear from some people I haven't heard from. I see Allie and Abby, Bradley, Riley. What do y'all think? Bradley says hydrogen +1 and oxygen a -1. But here's what I see. I got 2 hydrogens. So that means I got +1 and another +1. And I only have 1 oxygen. So if we give them Maria, says +1, -2. So if that oxygen is a -2, then a +1 +1, that gives us +2, and a single -2, that adds up to 0. So again, you're assigning the individual atom. Riley says, I'm kind of confused. I thought oxygen was 0. When it's by itself, okay, anything that's by itself. So if you had like a molecule of O2, Riley, yeah, oxygen would be 0. Anything that's by itself. When we write oxygen O2 because it's a diatomic molecule. That's why this chlorine right here is an oxidation number of 0. Okay, but the when it's in a compound, we know that oxygen is. Let me find a periodic table. Oxygen is main group 6. Okay, right here. And I already have it written in. Every element in main group 6 as an anion, they tend to carry -2 charge because they're gaining 2 valence to complete the octet. Yeah. So hopefully that helps a little bit. Let me go back down. So we've got everything assigned here. And again, I'm just going to erase all the extra writing. Whoops, I didn't mean to erase the -2 on the oxygen. So now we need to answer the question, which element is being oxidized and which is being reduced? So I see that oxygen's not changing. It's a -2 on both sides. So I'm going to ignore oxygen. Also, I see that hydrogen's a +1 on both sides. So I'm going to ignore hydrogen and oxygen. Neither one of those elements are being oxidized or reduced. What's changing, I notice, is that manganese is changing and chlorine. There's some chlorine atoms changing. Whitney says manganese is being reduced. So let's look at that. We've got manganese starting out is a +4, and on the product side, it's a +2. And I agree that the oxidation number is decreasing there, the charge is decreasing. So that is reduction. Chlorine is a -1 right here on the reactant side. Then you have, oh, we didn't balance it, did we? That was rule number 1. Balance. To balance this, I think I need a 2 right here, and then I think we're good. No, we're not good. Because we need a 2 right there.
So how does balancing like affect it if we were able to, are numbers different if we would have
No,
balanced it?
balancing doesn't affect you could still answer this question correctly without balancing it. I just realized the instructions said to balance it and we didn't. Yeah, but it won't mess up your oxidation stuff, redox stuff. Okay, so the chlorines. You've got all 4 chlorine atoms are a -1 charge over here. Then 2 of your chlorine atoms are still a -1 charge, but the other 2 are now a 0. So there's 2 of these chlorine atoms that are changing. Okay, so we're starting out as all are -1, and then some of them are 0. So that's increasing. -1 to 0 is an increase, so this is oxidized.
So you don't care about the chlorines that are negative on the product side?
The chlorines that are staying the same, we kind of ignore those. They're not changing. They're not being oxidized or reduced. You're
Okay.
only addressing the ones that are changing. And I think this is a great example because you can see sometimes you have the same element, but if you got to recognize you got 4 chlorine atoms here. So 2 of them are staying the same, 2 of them are actually being oxidized. But you would still say it's chlorine that's being oxidized.
Okay.
Okay, questions on this one? Okay, good. Thank you, Rachel. Good. We have even more. This is a different style problem. This is a chapter 6 problem. And I think it's the last one I have in the review slides. So we've got ammonia, NH3, and oxygen making NO and H2. This is also a redox reaction if you wanted to try to go through and figure that out, but that's not the question on this slide. Okay, the question is how much hydrogen in grams is produced from 25 grams of ammonia, which is NH3? So Allie says, can we do another example problem like the last one? Yeah, absolutely. And in fact, this one right here, after we answer this question, we'll also go through and see what's being oxidized and what's being reduced. Sound good? So when you read this problem, I hope you can recognize what needs to be done. What kind of problem is this?
A mass to mass ratio.
Mass to mass. It's one of those 3-part problems. So we're going to call this substance A. We're starting with the mass of substance A, 25 grams, and we're trying to figure out the mass of substance B. All right. Again, if you don't like the AB stuff, just don't worry about that. But to me, it helps me recognize, oh, I'm going to have to use that little diagram and do this step by step, 3 steps. So I know I'm going to need the molar mass of both NH3 and of hydrogen. Marie said, do we have to balance the equation for this? Yes, we do. And if we don't, we're not going to get the right mole-to-mole ratio, are we? So the instructions didn't even say that, but you do need to balance it. So what coefficients will we need to balance this? Maddie says 2, 1, 2, 3. 2, 1, 2, 3. Okay. 2, and then a 1 on the oxygen, and then a 2, and then a 3. That looks good to me. Going back to, so we'll get the mole-to-mole ratio in just a minute, but let's get the molar masses of NH3 and H2. I know we've got, okay, Abby says 17.04 for NH3. You guys are quick. So you just do 1 nitrogen and 3 hydrogens. Nitrogen is around 14 and each hydrogen is 1, so 17 makes sense. Hydrogen should be real easy. It should just be 2.016. And again, if you only use 2 decimals instead of 3, it's not going to matter, okay? I'll make sure Blackboard accepts the range of answers. A small range, but still a range. All right, then what is our mole-to-mole ratio between NH3 and H2? So we're looking at the coefficients here for this and this. So our mole ratio is 2 moles of NH3. Would it be H3? Whitney, what do you mean? For the mole-to-mole ratio? So 3.024? No, Whitney, we're just calculating the molar mass of H2. Okay, we don't take account the coefficient there. When we calculate the, okay. Oh, never mind. So for every 2 moles of NH3, we're going to get 3 moles of H2. And we'll see if we need to flip that or anything when we plug it in. You're good, Whitney, no worries. So now we're going to start the problem with 25 grams of NH3. Step number 1 is that you always plug in the molar mass of that first substance. So we're going to come over here, 17.04 grams will go on the bottom. And this is grams of NH3 for every 1 mole of NH3 times, now step number 2 is always the mole to mole ratio. And
Are you saying like this little chart?
uh-huh.
That's
Yes.
what you're doing for this problem?
Yep. So now I'm going to plug this in, and I want to cancel moles of NH3. I want to convert 2 moles of hydrogen so that after I do this, I can go from moles of hydrogen to grams of hydrogen, which is what the question's asking for. So I'm actually going to flip my mole to ratio and put 2 moles of NH3 on the bottom for every 3 moles of hydrogen on the top. And so far, I see that grams of NH3 cancel and moles of NH3 cancel. Last step, step number 3 is always the other molar mass. So the one we haven't used yet is the one for hydrogen. I want to cancel moles of hydrogen. I want to convert to grams of hydrogen. So for every 1 mole of hydrogen, it is 2.016 grams of hydrogen. So you'll do 25 divided by the 17.04 times 3 divided by 2, and then the times the 2.016. And Abby says she got 4.44 grams of hydrogen. If anybody got anything else, let me know. Otherwise, I'm going to assume that was what you get. Okay, so that's a 3-step problem. All right, now on the quiz from quiz 6, I had a question about, there was a problem. Oh, wait, before I'm getting ahead of myself, Allie asked if we could go over and do like another redox. So before I go to that quiz question I was thinking about, this is a redox reaction. What's being oxidized and what's being reduced? So we need to go through and put oxidation numbers on everything. I see oxygen by itself. So Riley, what oxidation number are we going to put on oxygen here? Exactly right, 0. Okay, NH3, this one even almost tripped me up the other morning, just because it's something we don't see a lot. But the oxidation numbers here, remember, you always put the positive oxidation number on the first element, negative. So we never see hydrogen being negative. This is why this one's like so, feels weird, but this should be a -1, and you've got 3 of them. And so you've got, let me make this smaller. You've got -1, -1, -1. So to make all this add up to 0, I only have 1 nitrogen. That nitrogen has to have a +3 oxidation number. Okay, on the product side, we have nitrogen and oxygen. Oxygen's like always hands down what oxidation number when it's in a compound?
-2.
Correct, Rachel. Thank you, Bradley. Yes, so nitrogen here is this feels weird too, but it's a +2. Because those have to add up to 0. You just got 1 each. And then hydrogen is by itself. So Riley, what do we give hydrogen here? She's got it now. Okay, so we got all the oxidation numbers assigned. So Allie, which one's being oxidized, which one's being reduced? This has got a lot going on, actually. I think all 3 things are changing. So nitrogen starts out as a +3, and it is going to a +2. Oxygen, she said, is 0, and it is going to a -2. So Allie, think about oxygen for a second. It's 0 on the reactive side, and it's becoming a -2. Riley, yeah, I'll scroll back down in just a second. So, well, here's the deal, Allie. When you have 0 and you're becoming -2, the technically the charge is decreasing, and that is or you could say it's being reduced. So this is reduced. And guess what? Nitrogen's also going down. So it's also reduced. Hydrogen is a -1 starting out, and it's becoming 0. So this is oxidized. So we haven't had one like this before where you've got all three things changing, but it's possible. Riley, is this let you see what you need to see? Okay, so yeah, there's that. I think that's it for that one. All right, last thing I'll say, and then we've been gone for close to an hour, right at. So if there's any questions, I'll stick around, but otherwise, I think it's probably a good time to take a break. I'm just going to zoom in on some white space here. We had in the quiz 6, I said, you got 10 milligrams of glucose. Now remember this problem? I said, how many moles is this? This is how many moles of glucose. What did you need to do for this problem?
You had to transfer milligrams to grams.
Okay, so 10 milligrams. You should have divided by 1,000 milligrams. That's 1 gram. And then what did you have to do?
Go from the grams to the moles.
Yep. So Kylie said in the chat, you got to use molar mass. Anytime you're converting from grams to moles, you have to use molar mass. So when you calculate the molar mass of glucose, I gave you the formula, C6H12O6. And when you add all of that up and look at the periodic table and everything, you should have got something like 180.16 or 156 grams of glucose for 1 mole. 1 mole of glucose weighs like roughly 180 grams. So you do 10 divided by 1,000 divided by the 180. And I think it was it was like times 10 to the -5, okay, or something really small. So that was that answer. But I think it threw some people off because we started with milligrams, and I haven't done that before. Okay, but you guys know how to convert milligrams to grams. You can do that all day long. Yeah. Thank you, Allie. It was like, yeah, 5.55 E -5, 10 to the -5. Okay. So, all right. Any questions from you guys before? Could you work one of the chapter 6 homework problems? Which one, Maddie? Let me get that pulled up. I'll do this, and then that'll probably be, I'll be surprised if my son is still sleeping.
Can I ask a definition question real quick?
Yeah, Rachel.
So for Avogadro's number, the 6.022, what is it? I just want to make sure it's how many, what that represents how many molecules are in a mole?
Uh-huh.
Okay.
Molecules or atoms. I think I'm about to sneeze. Maybe not. Sorry, excuse me. Yes, ultimately, it's how many items are in a mole. But in chemistry, what we always use it for is to calculate how many molecules or atoms. So if I said, you have hydrogen, how many hydrogen atoms, or that problem on the lab with the diamond, it said how many carbon atoms are in this diamond. And so that's how many, in that case, you're saying it's 6.022 times 10 to the 23 atoms in a mole. But if I said you had CO2, you have a gas tank of CO2, or you're a scuba diver and you have a tank of oxygen, then it would be molecules. You have this many oxygen molecules in my tank or whatever. Does that help? Okay. Maddie says, oh, hold on. Abby has a question. If you can't answer, it's fine. But do you know if on the test there will be fill in the blanks or multiple choice? Yeah, absolutely. There will be several multiple choice, and then there will be a lot of fill in the blank style stuff. Okay. I mean, this is no surprise based on everything we've done. You're going to have to balance equations, classify reactions. There'll be some redox stuff on there. You're going to have to do a 3-part problem. You're going to have to tell me, which molecules are polar and non-polar. You're going to have to look at bonds and things like that and tell me if bonds are polar or non-polar. So, what is the, okay, Maddie said the homework question she wants to look at is, what is the mass in grams? Oh, so I don't even have to pull up mastering. Hold on. Okay, the question is, I'm just going to go over here to a blank note. The question is, Bradley said, I have to leave. I have class on campus. This helps. Okay, good, Bradley. So glad to hear it. What is the mass in grams? We have 5.5 times 10 to the power 20 molecules of aspirin. C9H8O4. Yeah, if you got to go, you just head out. Thanks for joining us. All right, and it says, okay, what is mass in grams of that many molecules? Okay, so this is a 2-part problem. You've got to use both Avogadro's number and molar mass. So we need the molar mass of aspirin. So you're going to do carbon, 9 times 12.011. Hydrogen, I think we actually calculated the molar mass from lecture. I know we did this problem in lecture. Nope, let me go. Nope, not that one. I'm scrolling up because I remember doing this. Look at that. So we've got aspirin. Molar mass is right here, 180.163. We're just going to use that. So total, when you do all the hydrogens and the oxygens, it's 180.163 grams per mole. Okay. So first, we're going to take this number of molecules. I'm going to make this a lot smaller so that I can use some space here. And we have got to convert, if we're trying, it says, what is the mass? We're trying to convert to grams. So we're going to use this eventually, but first we're going to convert from, we're going to use Avogadro's number. Avogadro's number says there is 6.022 times 10 to the 23. And please remember, when you divide by Avogadro's number, it's this many molecules of aspirin per 1 mole. When you divide by Avogadro's number, you've got to put it in parentheses. Maddie says, for some reason when I did, oh, so maybe you just had the wrong molar mass. Well, we'll go ahead and finish it for anybody watching. Last step is for every 1 mole, you plug in 180.163 grams. So you'll do the 5.5 times 10 to the 20, divide by Avogadro's number, and multiply by 180 grams. 0.163.